who's the host?
Okay, so Владимир, можем? So we can start. Thank you.
No problem.
Yes.
Maybe I should make an announcement.
Yes. You should.
Okay, just okay, so today we have Yunfeng Jiang from the Southeast University, Yale Center, China, and he will tell us about the integrability in quasi-one-dimensional quantum magnet. Please start.
Okay. Thank you very much. So good afternoon, everyone. So first of all, I would like to thank Misha for the kind invitation. Actually, this is my first time to Russia in my life, and I hope I have a chance to visit in the future. Actually, you will see that this talk has many things that is actually, Moscow is a wonderful place to give this talk because many of the results mentioned here are based on this great Russian physicist. Okay, so I'm going to talk about integrability, which is mathematical physics, but I'm also going to mention about some experimental related stuff. So this talk is based on the following two papers, which is on arXiv early this year. And it's a collaboration with two groups of people. The first group comes from Shanghai Jiaotong University, led by Professor Wu Jianda and his student Wang Xiao and Yun Jing. And also another group in Renmin University, led by Professor Yu Rong and his student Ning Xi. Okay, so in the first part, let me give you some motivations. So what is this work about? We know there are several ways to do research in physics. So first of all, we have the experiments, and then we also have the theory. So we are all theoretical physicists here. And with the advent of computer science, nowadays we can also do a lot of numerical calculations and simulations. So as mathematical physicists, usually when we do research, we are driven by the pursuit of beauty and harmony. We just want to understand things, we want to see some beautiful structure. Especially for mathematical physics, it doesn't really matter whether we can explain experiments. But if your research, if the beautiful structures that you found in theory can actually be realized in experiments and in nature, then it's a double pleasure. And these moments will highlight, they are the highlights of theoretical physics. So here I'm going to discuss one of these examples, which is related to this talk. Okay, so it's about integrable models, like Heisenberg's spin chain. So it was first proposed by Heisenberg in 1928, and then solved by Hans Bethe in 1931 with the famous Bethe-ansatz. It's mainly about some one-dimensional or one-plus-one-dimensional models, and I think we are quite familiar with these models. They're out there for a long time, and then people would say that these are like one-dimensional models. After all, our world is three-dimensional, so it cannot describe real physics, real nature, and also our world is not integrable, because integrability is too good to be true. It has infinitely many conserved charges and can be solved exactly. So for a long time, people just treat them as some kind of toy models, where you can study mathematically and then have some fun. So, but in the past 2-3 decades, the situation has changed a lot. And nowadays, actually, they are quite experimental relevant, at least for a few examples. First, in nature, actually we find there are several one-dimensional or quasi-one-dimensional materials that can be described by integrable models. So some material whose low energy effective Hamiltonian is given exactly by the Heisenberg spin chain. Yes?
Sorry, I have a question. You're talking about one dimension, but spin chain, strictly speaking, in space it's zero dimensional. It's one dimensional in time.
It's like one-dimensional periods.
One-dimensional discretized space.
Yeah, it's discretized space.
Like lattice, one-dimensional lattice.
Yeah. Okay. So there exists some material whose low energy physics is effectively described by some integrable spin chains. So I will be talking about this kind of material in this talk. But I want to mention that nowadays there are also other experiments which are relevant for integrability. So you can do cold atom experiments. So in the lab, you can use optical lattice to model Heisenberg spin chain and also Hubbard model. And this is also now a very active research area for integrability. And yet another situation where you can use integrability is some superconducting quantum circuits that are used in quantum computation. And I didn't have time to talk about this today. So the key information here is that all these things that we developed in theoretical physics or mathematical physics can be quite useful in real material and in real life experiments. The thing is, usually there's a gap between people who do these experiments and people who do mathematical physics. So we are motivated to compute many things, but with different theoretical motivations. So they are really motivated to match the data with experiments and to tell experimentalists what to look for. So they will know exactly what to compute, and sometimes we compute things, but we don't know whether it's going to be measurable or not in real life experiments. Okay? So that's the motivation. Part of the motivation of my talk is to fill this gap, because I'm also doing mathematical physics, and in the past year, I started to learn about this experimental related stuff. So this is what I learned in the past year. So I'm not an expert yet, but I can try to answer some of your questions. Okay, so to explain the kind of physics that I'm studying, so we will start with a simple model, which is the Ising chain. So this is a famous chain. And this is the Hamiltonian of the Ising chain. It's a one-dimensional chain. So you see, you have a nearest neighboring interaction between sigma z and sigma z at site I and I plus 1. And if you ignore this, this will be the usual Ising chain. Now you add another field which is in the x direction. Okay, so you have this sigma ix. So this is called the transverse field Ising chain. If you look at this model, you'll find that at the zero energy, so let's consider the ground state. If this G is almost zero, namely very small, then this is the ground state of Ising. So you either have all spins pointing up or all spins pointing down. Okay, so you have this Z2 ground state. On the other hand, if this G is extremely large, namely this term is dominating, then the spins will tend to point at the x direction, right? So you see, when G is very large and G is very small, the behavior is completely different. So there must exist some value of G where you have some change. And this is called a quantum phase transition. And this is exactly what happens. So the transverse field Ising model is actually a prototype for the study of quantum phase transition. Because we are precisely at zero temperature, theoretically we are precisely at zero temperature, so this kind of phase transition is not coming from tuning the energy, which is the usual phase transition. We fix the energy to be zero, but we tune some parameters.
So G and H
is the same. Is the same. Yes. Yes. Just use different. So this is some graph from some experimental paper. Okay. So basically, you'll see that at some point G, you have a phase transition. Okay. And so this is this H, and in terms of G, it happens at G equals to 1. And this model has been studied already in the 1971 by Ferti. And it's actually, if you just want to find the spectrum, it's not hard. You just do the Jordan-Wigner transformation, and then we use a Bogolyubov transformation, you can find the spectrum. And indeed, you confirm that there's a phase transition. Now, as usual, if we have a phase transition, so we ask what happened at this critical point. So usually in phase transition, the critical point is described by some CFT because it's scale invariant. And in this case, indeed, the transverse field Ising at critical point is also described by a CFT. And actually is one of the simplest possible CFT. It is just the Ising CFT. So we're quite familiar with this CFT with a central charge, 1/2. and it has two relevant operators. One is called spin density, and the other is called energy density. It's a minimum model, simplest possible minimum model. Yes. And you have these two relevant operators. So this sigma x in the lattice corresponds to sigma iz, in the spin in z direction. And this energy density corresponds to sigma ix in the x direction. And these two in the conformal field theory, they are just some primary operators with the dimension delta, and the delta bar for sigma is 1/16, for epsilon is 1/2. These are the holomorphic and anti-holomorphic conformal dimensions. So we are quite familiar with this CFT. Okay, so everything is very good. If you want to compute something in the critical point, then you just use this simple CFT. Now, what about away from criticality? So if we are not precisely at the critical point, then this is in the continuum limit is going to be described by some different field theory. And we know from field theory, we can do relevant deformation and drive the system away from criticality. So because we have two relevant operators, so we can at least consider two kinds of deformations away from criticality. And they will be described by some massive quantum field theory. So if we turn on this epsilon, which is the energy operator, then because this is in the direction of this G, sigma x, because I said it's sigma x, so this just corresponds to the massive free fermion. Namely, in CFT is a massless free fermion, now it becomes massive. But it's still a free theory. Okay? So it's easy. Now what about turning on sigma? Suppose you turn on sigma, which is the magnetic deformation. This is more non-trivial. And this deformation has been studied by Zamolodchikov in the 1990s, actually in 1989, I think. So there he found that if you do this magnetic deformation, you will also obtain some massive quantum field theory, and this is the famous Zamolodchikov's E8 theory. It's not free anymore. It's an interacting integrable quantum field theory. Yes?
Sorry, I'm confused. So the first deformation, you introduce the magnetic field in the x direction, right?
Yes, yes.
But you do not call it magnetic deformation.
Yeah, because this in the CFT corresponds to the energy.
The second one is called the magnetic deformation. Can you interpret this as a magnetic field, but in different direction? Right?
Yeah, it's in the sigma z direction.
In z direction.
Yeah, it's in the z direction. Yes. Okay. So this is a famous work by I think is Sasha Zamolodchikov. So he predicted that if you do this kind of deformation, you will reach at this integrable massive quantum field theory. And of course, you can try to do both. If you turn on both epsilon and sigma deformation, you will also obtain some theory, some massive theory, but it's much, much more complicated. So this theory is not integrable anymore. But still, it's interesting. I think even in the 2006 and 2010, such as Zamolodchikov and collaborators still working on this spectroscopy of this kind of theory. So our main concern will be this E8 theory. So this in the lattice corresponds like this. We turn on this magnetic field in this sigma z direction by this Hz, which is related to our H. So you'll find that by Zamolodchikov's analysis, this theory will contain 8 stable particles.
So this sigma x is just at the value that you see in critical point, yeah?
Yes, this is a critical point.
So you turn off magnetic field here on a critical point, so this is conformal point, and you switch on magnetic field.
Exactly. In the z direction, yes. If I switch magnetic field in x direction, it just pushes it a little bit away and become massive, but still free. But if you do this, it's not free. It has this 8 massive particles with this mass, which are related to each other. So basically, they're all given by m1 and m2. So you can remember this table, especially this one is important. This one is telling you that the ratio between M2 and M1 is actually the golden ratio, 1 plus square 5 divided by 2. Okay? Now, why it's related to this E8, the algebra? Because Zamolodchikov pointed out this is related to the total field theory based on the E8 algebra. And because of this, the mass spectrum, which we just see now, is actually an eigenvalue. It is actually the eigenvalues of this matrix, where this alpha j are the simple roots of E8, of this Lie algebra E8. So this qi are some integers that are related to the total field of E8. So you can see this is already some non-trivial quantum field theory.
Yeah, so R is what is rank of... What is R?
R is the rank of E8, so here it's taken to
R
be
is equal to what?
to 8, in this case.
And why, so this is 9, then I from 1 to 9, it's written some.
It's more, actually to explain this formula you need a few more slides, so you also introduce some maximal root or something like that. But R goes from 1 to...
So that's because this is a fine code actually.
It's not yet defined, this is not defined.
This is diagram thinking of a finite dimensional total, but you use some rules of a fine one.
You can introduce a fine one, just to parameterize this matrix, Okay, but anyway, just E8 simple root.
The one you mean, which is usually denoted as rho, right?
Yeah, usually you make a combination of the rest of the roots and then...
I think maximum is 30, is what is denoted by 30, not by rho. And rho is rho is half of the sum of positive roots, of all positive roots. Sometimes they coincide, but probably sometimes not.
Yeah.
So this maximal root is related with a final, right?
Yeah, it is related, yes. So it's like this.
Who's qi in this formula?
Qi is some integer that's related to this E8 toda.
A bit strange for me, the formula, because, well, usually in toda, everything is written in terms of Cartan matrix, right?
Yeah.
But this seems not to be a Cartan matrix.
You can write it in terms of kata magic. It's the usual toda. It's nothing new. It's just I choose some.
Yeah, because since this is still in the case, Cartan matrix is very simple without. Okay.
It's the usual story. It just I just use some strange notation, which I take.
For you some notation.
Yeah, because it's short. I just want to make this point. Yeah, you can diagonalize this matrix, which is related to E8, and that gives the spectrum. So we want to see whether this kind of thing, you can see it in experiment. Because to construct this E8 toda model is really from mathematical perspective. You don't really expect that it can be really useful in an experiment, but you'll see because it's related to this deformation of the simple Ising chain, so then it can be somehow related to experiments. Okay, so to summarize, actually this theory will have interactions of A type of particles with those masses, and the scattering is factorized because it's an integrable theory, and also it's diagonal. There's no backward scattering. So the non-perturbative S matrix can be found by the S matrix bootstrap. I will say something about it. So it can be found by bootstrap. So basically this means you can use integrability to solve this interacting theory completely. And this is the development from the theory side. Okay, so what about experiments? A breakthrough is this science paper, which was published in 2010, where they look at this material. I don't know how to pronounce it, but it's COMB206. It's kind of this kind of material, and you find that this is the low energy effective theory of this material is described by the Ising chain. So you can tune this magnetic field to reach the critical point and away from critical point. Okay? So let me just say a few words very quickly about how these experiments are done. So suppose you take this material. What do you do? What do you measure? So the experiments that these guys are doing is doing some neutron scattering experiment. So you prepare the sample here, and then you just shoot neutron at it. Then the neutron will get scattered by this material, right? Because this energy and momentum will change. And then you will just, like doing the usual scattering experiment, you just measure the outcoming, the cross-section of the outcoming neutrons. and measure their energy, their momentum. Basically, you measure the energy difference and the momentum difference because the incoming beam will have a fixed momentum and energy. And then basically in experiment, you measure these cross sections of these neutrons. And then by Fermi's golden rule, you can relate this scattering, you can relate this cross section to some matrix element. And this is related to the property of the target. And this matrix element, by doing some simple calculations, you can find that by linear response theory, this is related to some correlation functions, or more precisely, the Fourier transform of some correlation functions. And this is the part that we theorists need to compute, because they measure cross-sections, and from there they can extract this Fourier transformed correlation functions. And our task is to compute this thing for different theories. Okay? So more precisely is this guy. This is what is called a dynamical structure factor. We will talk about this a lot in this talk, and it's the short DSF, dynamical structure factor. So what is this? This is just you take an operator in the field theory, say, then you compute its two-point function at different space and time, and then after this you do a Fourier transform with respect to t and x. Then this will be a quantity depends on omega and depending on q. So this is essentially the Fourier transform of two-point functions. And in this material, or in this study of this material, we are concerned with local spin operators, because this describes the spin dynamics. So you want to evaluate, basically you want to take O, correspond to this spin, sigma x, sigma y, and sigma z. Okay? So how do we compute it? Because usually in interacting theory, computing two-point functions or correlation functions in general is not an easy task. So on the lattice side, so remember this, on the lattice side before taking the continuum limit, this is just a one-dimensional chain. So for the one-dimensional chain or one-dimensional lattice model, nowadays there are well-developed numerical methods like DMRG or ITEBD, where you can compute not every the ground state two-point function. So it's DMRG, and this ITEBD is very good for computing the ground state properties, but not for excited states.
How does ITEBD spells? What is it for?
I also forgot. This is not my part. Yeah, that's the matrix.
I've never heard about.
This is T is the time.
Density matrix randomization group.
Yeah, density metric randomization group, and then this is time evolution, imaginary time evolution bisecting the last one I forgot. Yes, it's some numerical method, and it's very efficient, and some of our guys does this. Okay, so this means that using this tool you can compute the lattice two-point function and the lattice DSF. So this gives some data. And what about field theory? Now, for generic quantum field theory, a two-point function, non-perturbatively, I don't think there's a hope you can compute it. But if the theory is integrable, then it's possible to obtain some non-perturbative results by using the form factor bootstrap approach. And I will describe what this approach is. So now I will give some time to describe the form factor bootstrap approach. So remember we are in 1 + 1 dimensions. So if we are in 1 + 1 dimensions, then we have very simple kinematics. The energy of a particle is just given by mi cos theta, and the pi is given by, the momentum is given by mi sinh theta. So if you take e squared minus p squared, you have m squared. So this gives the correct dispersion relation. And we will call this theta the rapidities. So essentially you can imagine this theta characterize the momentum and energy of a given particle. And so the Hilbert space will be spanned by this n particle asymptotic states. So you have the vacuum, you have the one particle state, two particle state, and so on. So this will span the Hilbert space. And in our E8 theory, you have 8 types of particles. So AI goes from 1 to 8. So suppose you want to compute this two-point function, then what you do is that you insert a resolution of identity here. which decompose this into a sum of the product of this object. And each one of these objects is called a form factor, which is basically a matrix element between vacuum and some excited state.
I'm sorry, about this particle content of the series. So, for example, in complex Sich-Gordon, you have the composite particles.
Yes.
But here, all these particles are in the elementary matrix, right?
They scalars.
No, they also exhibit in poles. So you need to close the bootstrap.
Okay.
You need to close the bootstrap. Yeah. Because in integrable QFT, you need to take all this into account. Okay, so now how to compute this thing? This is related to another set of very beautiful theoretical work. It's about solving a quantum field theory. So suppose you want to solve, what does it mean to solve a quantum field theory? I think broadly it means that the ability to compute all the on-shell quantities like the S matrix and all the off-shell quantities like the correlation functions, non-perturbatively. So it's not doing Feynman diagram order by order. So of course, if you want to achieve this is very ambitious. You cannot do it. Basically, it's hopeless to do it for generic QRT. But if the theory is if it's a 2D CFT, maybe you have some chance. If it's a 2D integrable quantum field theory, then you also have some chance where you can achieve these goals. So usually, for solving integrable QFT, there are two steps, and the idea is called a bootstrap. So the first step is called S matrix bootstrap, and the second step will be called the form factor bootstrap. So the idea is the following. Suppose your theory, your quantum field theory, is integrable. This would mean that any n particle scattering process will be factorized into a sequence of two particle scatterings. And because it's integrable, so there will be no particle production. So it's actually going to be a sequence of 2 to 2 S matrix. So this means all the dynamical information are encoded in the 2 to 2 S matrix. And then if you can determine this, you are in a good shape. So basically all the S matrix, you just need to determine the 2 to 2 S matrix. And the way is not by doing Feynman diagrams. Instead, we impose some general requirements for this S matrix, which includes unitarity, crossing symmetry, and importantly, Yang-Bak's equation for integrable quantum field theories. And then you also make some assumption about analyticity of this S matrix. Then it turns out with some perturbative input, this is necessary because you need to know which theory you are solving. Because all the S matrix will satisfy this. So to distinguish which theory you are solving, you need some perturbative input and some other input. So it turns out this approach works quite well in 1+1 dimension, and then you can actually find the S matrix of many integrable theories. And this is pioneered by the two Zamolodchikovs in 1979.
Isn't it possible that some abstract S matrix does not correspond to any good perturbative expansion?
It's possible, yeah. Actually, by bootstrap, you find many solutions, and it's a non-trivial job to relate an S matrix to certain known. Yeah.
Sure,
yeah.
I'm not sure that it is, how to say, well-defined job, yeah?
Yeah.
That you always find a solution, because in principle, it can be that there are no degenerative expansion corresponding to some S matrices.
Yeah, I agree.
I don't think
It's possible.
I
Yeah.
know.
Exactly.
Mm. Yeah.
Are there any examples?
Yeah.
I mean, various matrices you can solve. I mean, there is so-called CDDM you use. You just multiply by some factor, and that doesn't correspond to any local feature.
Yeah, that changes the UV behavior completely. Yeah.
Well, right. I mean,
It's great and
I
that.
thought the question was as follows: like, if you have like in some sense, like a well-defined 2D QFT, right? And you know an S matrix, but it doesn't have a perturbative expansion.
Well, it depends what you ask, why well-defined QFT. I asked just to take some S matrix, it may not correspond to some well-defined perturbative QFT, if you wish.
Mm.
But after what Lёша said, better to say up to this ambiguity. Is it obvious that using such ambiguity you can relate any solution to n boxer to a perturbative QFT?
Well, if you can solve like TDA equation and see that the energy scales are all the way down to UV, then at least you can.
Well, you can extract some information like central charge, but the content of these operators and then what the Lagrangian looks like, this is not obvious from just from solving the S matrix.
Extracting effective central charge, so the central charge minus.
Yeah. Indeed, yes, exactly. Yeah. So this is like, in some sense, the shortcoming of the bootstrap method. So you don't know which theory you are solving. So, but in many cases that our favorite theories are actually, we know them, and then we can identify this S matrix. So this is the first step, very briefly. Now suppose you solve the first step, it means you have solved all the on-shell quantities, then you want to compute correlation functions. Then what do? The idea is to use this form factor bootstrap approach. So as we said, you can decompose first these correlation functions into matrix element of local operators, and then you can compute these matrix elements using the bootstrap idea. So the idea is, again, you impose a set of axioms that you think a form factor should obey, and then you try to solve these equations. And then also you need some input. So this is our two-point function. This is the form factor. And again, this is the resolution of identity for IQFT is particularly simple. And then, okay, so how are we going to solve this?
And in these two formulas is different, right? And in the top formula is different from n.
Yeah, sure, yeah. Okay. To explain these axioms, let me make some diagram. So you can imagine this form factor will correspond to this figure, where this O will be the operator, and these legs are the incoming particles with rapidity from theta 1 to theta n. So we want to compute this guy. So here, for illustration, for the simplicity of explanation, I just consider the theory with one type of particle, so which is simpler. But the idea works for multi-particle scattering. So what are these axioms that you want the form factor to obey? The first axiom is called the Watson's equation, because in one dimension you always have to order your particles, because if you want to cross, you have to scatter. So if you swap the order of these two particles, red and blue, theta I and theta I plus 1, then it tells you that the price you need to pay is an S matrix. And this S matrix is actually the S matrix that we found in the previous step. So you have to solve the first step first. And then this S matrix will come in as an input. So S matrix enters here. So this is the first equation. And the second axiom is called a cyclic permutation. It just tells you that if you move this one to the last position and shift by 2 pi I, then you should obtain the same form factor.
It shouldn't be consistent with the previous one?
Yeah, it should be.
And does this impose any restrictions on the S matrix?
It will be satisfied, yeah.
Why by minus 2 pi I?
Yeah.
Energy and momentum doesn't change, yeah, according to your definition.
Yes, I think these axioms first it was proposed by Weiss and Karofsky, then studied systematically by Smirnov. So the idea is that they first really studied these form factors by computing Feynman diagrams, and then they find that the things they obtain obey this kind of relation. So they just extract, reverse the logic and say, let's formulate this and then see whether we can solve analytically.
Even on this level we don't understand, yeah? Because it's some non-analyticity, yeah? Since it's as a function of energy and momentum.
Somehow
Just
what
the
is
same.
going to now, there is a cut in this group explain, right? And I mean, in terms of theta, there's just this.
It's a fundamental strip.
Yeah.
Yeah.
But this
Yeah, so let's go to our physical state.
yeah, so on the plane of momentum, momentum, you go under the cut. But why? I don't remember.
I also don't have a deep understanding about this, but this one.
That's also for complex.
Yeah, I mean,
Yeah.
it's
Of course, these are functions.
yeah, it's analytic function in some string, some domain.
Yeah,
Of course, I mean, real theta correspond to like real.
the physics. Yeah, but you need to do analytic
I
continuation.
mean, even first relation, right? Because the form factor is defined that theta I is smaller than theta I plus 1. But then, if you permit
Yeah,
them,
then it's not in the physical region. It's not as asymptotic state. Yeah.
yes,
Yeah. Okay, so this is the second one, and the third one is called kinematical singularity. In the graph, it means somehow if you have two rapidities with the difference, which is I pi, then your form factor will have a simple pole. And the residue of this pole is related to the form factor with two particles less. So in terms of diagrams, it just means that if this particle can go straight, it can, you can remove it either by just going through, or it scatters with everyone and then go through. So this is kinematical singularity is only due to kinematics, so it has to be obeyed for all the theories. And then you also have this dynamical singularity, because we know that in theories with bound states, you will see poles in the S matrix. Now, suppose imagine you have the situation where these two incoming particles has the correct energy to form a bound state. Then you will also see this singularity. So this is the dynamical singularity because it's related to the dynamical property of your theory. So this IU will be this place where this S matrix has a pole. And then this gamma will be related to the residue of this pole of the S matrix. So information of the S matrix also enter here. Okay? And
in the previous case, this pole was not related with any bound state, yeah?
O? Which O?
No,
Could be
on
kinematical.
the previous.
Yeah. Yes. Kinematics is not related to any bound state.
Because by plus I pi, it means that the momenta are like that, yeah? And
Yeah.
they just coincide.
Yes.
So they make a pole,
But it's not related to particle content. It's true for everyone. So that's why it's called kinematical pole. And this is dynamical. Okay. It happens at a specific point. And with these axioms, you then also assume the maximal analyticity assumption. Namely, the form factors, they are meromorphic functions of the rapidities, and they only have singularities prescribed by the axioms. So it's either a kinematical pole, if you see a pole, it's either kinematical or dynamical, or coming from the crossing symmetry of these poles. So then, because all the operators, the form factor of all the operators have to satisfy the same set of axioms, then how do you tell which operator are you considering? The form factor of which operator you are considering? So therefore, some extra input are needed when you solve these equations. And the extra input will include something like the vacuum expectation value of that operator. And also, you need some asymptotic behavior of these operators. For example, if you take the UV limit, if it's given by a CFT, then you can read off some. Then you know this two-point function will be given by a power law with some dimension delta. So this also gives you some restriction of the form factors. And also, once you solve this equation, it turns out that in many cases you can solve them. And then you can find form factors, but that's not the end of the story because you need to check whether what you obtain makes sense. So usually careful checks are done. So with other methods, for example, you can use this truncated Hamiltonian space method, then you can check whether it gives the good result. Okay.
Sorry, can you ask about, can you clarify about the asymptotic behavior? So what exactly should they check? Because you're talking about number one dimension, you're talking about a two-point function, right?
Yes.
But the form factor is basically a one-point function in a sense, right? So you only have one.
Yes.
Right? So what kind of image should I take for a form factor?
For example, it will be related to, for example, when you take these thetas to infinity, to very, very large, it should be constrained, whether it grows like polynomial or it grows exponentially or it's, what kind of growth that you need to impose. So this kind of information can be extracted when you consider 2-point function. So you imagine you can take these 2 points very close to each other, then this is described somehow like a CFT, and if they are very far away from each other, then this is clustering. So it just become, yeah. Something like this can tell you what do you expect when theta is very large.
Yeah, but of course, I mean, the expansion doesn't work in the UV administrative universe. Certainly,
Yeah.
You cannot, like, in order to go to the UV, you have to sum all the series.
Yes, yes.
In principle, but
Yeah.
I mean, numerically, you can like predict the UV slope of this. I don't know.
Yeah.
I just this is like a simple way to say it. You're saying that the form factor should go predominantly or something with theta's.
Yeah.
Like the degree of this polynomial.
Yeah, the degrees of polynomial should be bounded by something. Yeah. Yeah. That's true. Yeah. That's related to the same.
And then the truncated method, how you can use it.
So the truncated Hamiltonian space is that, so suppose you know your integrable QFT, the UV is described by certain CFT.
If you know.
If you know the CFT, yeah, then you can do that. It's using some TCSA. Yeah, because TCSA is very good when you are near the critical point, and this approach is very good when you are in the IR, because then you just take a few sums, it converges quickly. But there are some range of energy where these two overlap, and then within this range you can compare.
I mean, here you can try to do the conformal postulation. You just don't need to use the Hamiltonian truncated Hamiltonian.
Yeah. You can do all kinds of checks, and then this is a common practice. Like people in Budapest, they like to do this a lot. They, the last approach, yes. Use this and then compare, because this gives some non-perturbative data, and then you can check. Yeah. Okay, so just very briefly sketch, because these equations doesn't look super easy to solve. So usually one of the strategies is that, okay, you can make an ansatz to solve this equation. So this is the ansatz you can make. So I'll explain this. So this is called the minimum form factor, and it's described by it's completely determined by this S matrix. So there's a theorem. If you give me the S matrix, then I can just use this theorem to find this minimum form factor. What does it do? It basically takes care of this Watson equation, because when you swap this, it will give an S matrix. And then this denominator will take care of the kinematical singularity, because you see if this sigma j is a sigma I plus I pi, you have a simple pole. Okay, and then when you take this, when you take the residue of this pole, this will give you something, and then this will relate this q, which is a polynomial in exponential theta I. And this will, the kinematical singularity and dynamical singularity axioms will give some kind of recursion relation for this Q.
So dynamical singularities are contained in minimal form factor, right?
So what?
I mean, dynamical poles, they are in the F minimal.
Yes, it's also contained in, yeah.
Dynamical.
Yes. So you see, you need to solve this Q. And then the asymptotic behavior will be used to restrict this Q, because you need to assume some analytic behavior of this Q, and then you can solve them with this assumption. You can solve them recursively, and then this H, and then because it's a recursive relation, so you need to have some starting point, and the starting point is the input of that operator, like the vacuum expectation value of that operator.
Even if you have a starting point, there's still some.
Still, there will be CDD factors and so on.
Yeah. There's like I don't know, like a kinematical equation that has a kernel. There's some functions which still map to zero. No?
Yeah.
I mean, in terms of polynomials, so it's not. I mean, the initial polynomial does not provide.
Yeah.
Solution.
Yes. Not exact. Yeah. So this is just a very brief sketch. Actually, to make this thing work, you need to put in a lot of effort. I know someone like Babu Jiang work on this for the whole life almost. Yeah. Yes.
But, sorry, I just probably missed. So this is some kind of a solution of this requirement, but this solution is, well, it just kind of, you have to find it from nowhere, yeah? You have somehow to write some answers, yeah?
No, not nowhere. I'm just saying here, this F minimum, you can uniquely determine from S matrix. So this part fixed. This denominator is also fixed because it takes care of the kinematical poles. Then you have this polynomial. Then you have this Q, okay? Yeah, polynomial of e to the theta. So, and then, so which power should I truncate if you assume it's a polynomial? This will come from some asymptotic behavior of the 2-point functions. And then there is some constant h. So this will be related to like the initial values of things. So it's an educated guess.
The polynomial has many coefficients, so they...
So then you try to determine them recursively by, yeah.
Symmetric polynomial is probably some.
It's slightly easier. So you can do like 1 particle, 2 particle, up to some particle value. Then you can guess a general form of this guy, like written in terms of determinants, and then extrapolate.
Symmetric only if you have one type of particle.
Yeah. This is one type of particle. This is already simple enough.
Yeah, this is only particle number one.
Yeah. If you have more complicated theories like ON sigma model or sine Gordon, then the story will be considerably more complicated.
And here in E8 model.
E8, but it's diagonal scattering, so it's very simple. Well, it's simple, not extremely simple, but the non-diagonal scattering, like the sine Gordon, this is really a pain. Yeah. So you need some more advanced techniques to find these form factors. But the information I want to convey here is that for many integrable quantum field theories, you can actually do that. And it has been done. Okay? So I'm a bit far from the experiment side. Now let's go back. So this is just a detour telling you how you can find the form factors. Now suppose you can do that, say for EA model, which has been done. Then you want to look at this DSF, the dynamical structure factor. So remember, this DSF is just the Fourier transform of 2-point functions. So of course it can be written in terms of form factors. And then this Fourier factor will give you these delta functions. So then this is just the sum. And then here, because you have multi-particles, so I need to keep in check how many particles of given type I have. So this is the slightly complicated looking of the dynamical structure factor. So here I just denotes the sigma I. Okay, so this is my form factor. Suppose we can compute it by the bootstrap method, and it has been done. Now you should try to expect what should I see from experiment, right? Theoretically, what does this look like? So for simplicity, we just consider Q equals to 1. So where Q is here, the total momentum. So let's consider the Q equals to 1 situation. And Q to 0, yeah, Q to 0, sorry.
What's so special about 1? Just a single factor, yeah?
Yeah. So then I'm going to analyze like 1 particle, 2 particle, because typically in your calculation of this kind of expansion, you compute 1, 2, 3 is a lot particles, and then you will see that the multi-particles 4, 5, they just contribute very small. Their contribution is very small. And then so let's see what kind of signals we are supposed to see. Suppose you take just 1 particle, the 1 particle contribution.
Very small for small frequency, right? I mean, where it is small.
Yeah, you'll see a picture soon. So suppose I take Q equals to 0, N equals to 1. Then I have 2 delta functions, right? And this delta function will tell me that theta is better to be 1. So then I can get rid of this theta, and then I still remain, 0. 0, yes, theta equals 0, and then I still remain 1 delta function. So this will be a sum of delta functions, pure mathematically. Yeah, because you have 2 delta functions, 1 integral. So you are left with sum of delta functions.
You have sum over the type of particles, yeah?
Yes.
And only with delta functions, their masses.
Yes, precisely. That's what you should find, right? So if you draw it, you should see a sequence of sharp peaks just from the 1 particle contribution. And that's what you should see. And that's one of these figures. In this paper, they calculated these E8 form factors. So the first, the one particle contribution, you should see very clear sharp peaks, and in particular at this mass of these 8 particles. So if you can measure these guys in experiments, then you can tell whether you are having these E8 particles or not. Now 2 particles, slightly more complicated. Now you have 2 delta functions and 2 integrals, but still you can compute it. Suppose this form factor you can compute it either numerically or analytically, and you will find now it's more continuous because it's not the sum of delta function anymore. And then it still have some peaks, but this peaks is given by this, you need to evaluate this form factor explicitly. And you see there will be some peaks like this, where this P2 is M1 plus M2. So you see the contribution starts at this 2 particle threshold. So it contributes like this. And then
they are able to experimentally extract these different contributions.
You'll see. You'll see. So this is 2, and then 3 and 4 higher particles, you'll start to see some continuum because you really need to integrate. But you can see, so here the contribution in some unit is 0.76. So the 4 particle case will already be 1 magnitude of order smaller. So the contribution is getting smaller and smaller. The dominant one will be the 1 particle, 2 particle. And then from the previous 2 slides, you should imagine what you should expect. You should expect a bunch of peaks. And the position of these peaks are related to the masses of the particles of your theory, right? So that's what we're supposed to see. So if you sum over these expansions, sum over these first few terms, that's what you get. So this is the result from the form factor calculation. So you will see this peak, this peak, this peak. Okay?
3 orders, right?
Yeah, you take 3 of them. Yeah. And so this is the from numerics. Namely, here you take the Ising chain, you use this numerical method, also compute this dynamical structure factor. And you compute them numerically, you feed them, you find these peaks. So this matches well with what you find in field theory. So that's the theoretical prediction. It's just sometimes the position of the peaks are almost identical, but this amplitude can be different due to some additional numerical effect and the zone folding effect. Okay, so that's what you are supposed to see if you do experiments. And experimentalists, they can measure this.
This numerical.
Yeah.
Yeah, numerics is done for spin for finance.
For the chain. You can usually you take like 100 or 200 sites, and this is a good approximation to the field theory calculation. If you take like 10 sites, probably it's not enough. Yeah, because there will be finite size corrections. Okay, so these are our theories. Okay, and what about experiments? So that's the experiment. You see, these are the experimental data, and indeed they measure this intensity, they measure this dynamical structure factor, they see some peaks, but because experiment you have error, it's not completely exact. So you need to take this into account. So what they do is they measure the ratio of these peaks, M1 and M2. So remember, M1 in this E8 theory, M1 and M2, their mass ratio is given by the golden ratio. Okay? So that's what they try to measure. Is this given by the golden ratio? And they found that, okay, indeed, in this correct parameter regime, is very close to 1.6, which is the golden ratio, which is this one.
B of t.
B of t means that you need to increase the strength of the magnetic field to some proper regime, then you can see this effect more clearly. Okay. So, and you see, they indeed measure this, M1 and M2, the ratio of them, and find it's approaching this 1.6. So that's why they claim that this is the first experiment that observed the emergent EA physics. Okay, so the point is that what they measure is this dynamical structure factor, and then if we want to be useful for experiments, then what we need to compute are actually 2-point functions. You need to know how to compute 2-point functions, do the Fourier transform, then you can explicitly compare with experiments. So that's our task. Okay, Yeah, so this was considered to be a big breakthrough because EA theory is complicated, it's integrable, it's from mathematical physics, but somehow you can realize that in a real material. And that's 2010. Now, after 10 years, there are some better experiments. You can also, there's another group of people in 2020. They do another experiment, measure the same kind of, yeah.
Experimentally, so what is the main problem is somehow to extract a piece which would correspond to this excited Ising model, yeah?
Yeah.
And so what is the idea? How do they know that they will get Ising and this E8 in experimental situation? Because as you say, there are some neutrons, whatever, and there are neutrons and there is Ising here.
Yeah, this is also a mystery to me. So I know that this is not the only material described by this Ising. There are also some other material described some by XXS spin chain. So people doing experiments, they have their way to find it, but it's not, their starting point is more like starting from Ising, just to see that what kind of material first in one direction has the strongest interaction, and then the rest too, because all the material essentially are three-dimensional. So you need to find some effectively one-dimensional material, and there are not so many of them. And then if you are experienced, then you know what kind of material you should look for. So that's the secret from experimentalist. I don't know. But this is this material is actually quite famous, this COMB06. And people know one should look for that if you want to describe the Ising. So what's new is that you know that away from criticality, it will be described by E8. So then you should look for this E8 physics. So how do you look for E8 physics? You measure this DSF, you extract these peaks, and then you compare the ratio. So if you need to get very accurate data for this neutron scattering experiment. And you need to keep the temperature very low for doing that, because we are computing zero temperature form factors. If you have increased the energy, then will be a thermal fluctuation, then you won't see this physics so neatly. So all this needs some special techniques, and that's the value of this experimentalist.
Can I also ask a question? If you have, like, say data like this, but maybe more precise, like what you described in the next slide, apart from the mass spectrum, can you compare it to like something else with the E8 theory? Like, say, can you find maybe the scattering phase or something like that from this data and compare it? Or just, well, I guess the mass spectrum is like more robust, right? It's, you can see these peaks, but...
Yeah, so far, I think in this material, it's already a great achievement if you can measure all this mass, because so far in 2010, they only managed to pin down M1 and M2. And then the rest data is actually a bit blur. If you want to confirm it's exactly E8, you need to be able to determine all this exactly, all this M3, M4 to M8. And this is already a very difficult task. And without this data, without this very neat data for the spectrum, it's probably a bit hard to extract other things. But in cold atom, in some other experimental setup, you can do a bit more. You can measure other quantities like the transport properties. In cold atom, you can measure how the spin transport, how energy gets transported, and then so on and so forth. So in different experimental setup, you measure different things. So here, the simplest measurement, or the neat measurement, is to this dynamical structure factor. And already to have this is non-trivial. You need to compute form factors. And form factors contain S matrix, information of the S matrix. Yeah. Okay, so I'm just saying for this, yeah, it's already non-trivial to just measure this, these peaks. Now, after 10 years of this neutron experiment, so then the experimentalist, another group of experimentalists study the same material, but with a different approach. They use this high-resolution terahertz spectroscopy. So instead of scattering with neutrons, they scatter with photons. And then they can also find these peaks. But with this more accurate data, there are some puzzles. Because apart from these peaks that we believe, that people used to believe, this corresponds to E8 particles, they also found some new satellite peaks, which are observed. So this experiment just gives a bit more peaks. And these peaks are not really explained by E8 physics.
But how can you say this cannot be attributed to these higher terms?
The higher terms, you can compute them theoretically. You will find that first they form this plateau, or it's a continuum. They don't give peaks anymore for the higher terms.
Right. You do not have the result for arbitrary n, right?
But it's easy to extrapolate. It's easy to extrapolate. If you come 3 particle, 4 particle, yeah.
Many particles that would be
Yeah. It's,
some plateau.
yeah, it will be, of course, logically you say, okay, why not? But it will be strange if you say at 17th particle, suddenly you got a peak. But I don't know. So that's what we expect. But the truth is that, okay, with this new data, you found some peaks that you cannot explain by E8, or cannot explain very well by this E8 physics. So this raised the natural question, is the Ising universality and E8 physics enough to explain this material? And that's the question that we are doing in this new work. Okay, so now is this third part, is a tale of 2 Isings. It's no longer just 1 Ising. So E8 is like 1 Ising away from criticality. Now, this is a more realistic picture of this material. So this is the A and the B direction, and this is the C direction. So you should imagine you are looking from this side, then they look like this. And then in this direction, the C direction, you will see a chain. This is the Ising chain, okay? Imagine that. Now, this is a chain, all these are chains. But then there will be couplings. In fact, in reality, there will be couplings between different chains, right? So there will be some couplings like this blue J, and couplings like this red J. And this red J is bigger than this blue J in this direction. So, in fact, you need to see whether this interchain coupling can affect your theory, can affect this form factor computation and so on and so forth. So in this work, what we're doing is try to incorporate this interchain behavior, this interchain interaction, and see what's the difference between the standard EA physics. So that's a question. That's a theoretical question. And yes, so the key thing is to take into account some interchain interactions. And that's it. So we will keep the full Hamiltonian is the following. So you have the Ising Hamiltonian for one chain, for another chain, and then you couple them in the z direction. So this is sigma 1z is one chain, sigma 2z is another chain. So you couple them side by side with some coupling constant lambda. And for H1 and H2, we keep them at criticality. So this will still be 2 critical chain, but you couple them, so this will be a deformation away from criticality. So the 2 chains are at critical point, and we want to compute DSF. The reason is clear. We want to explain this experiment data. And for the lattice model, you can again do it by this numerical method. So there's no essential problem. So what about the field theory? What kind of field theory that describes this? And for that, we need to go a little bit in the standard method of condensed matter physics. So to solve Ising, first you can do the Jordan-Wigner transformation, because this is a transformation where you transform the spin operators to fermionic operators. And this is a non-local transformation. There should be a -1 here. I missed it. So once you do this transformation, write this sigma j and sigma x in terms of Cj and Cj dagger, you find that the Cj's will satisfy the standard fermionic commutation relation. So then you can reformulate a spin chain in terms of some lattice spinless fermion. And with this fermions, you can build some fermionic field like this. So this A is the lattice spacing, And then you can build this psi L and the psi R. Putting them together, this gives a Majorana fermion, the two-component Majorana fermion. These are standard techniques in this Ising model. Now we have two chains. So for each chain, you can build this Majorana psi. Now you have two chains, so this will be psi 1 and psi 2. We can combine these two psis together to make a complex Dirac fermion, because these psis are Majorana fermion.
Yes, strictly speaking, they commute over the
Yes, indeed. That's an important point I want to make. Yeah. So you need to take this into account. But before that, let's pretend we just proceed and see what we get. So if we proceed, then we can write this psi. Also, is a two-component spinor. And here we can use the so-called bosonization, because in one dimensions, you can transform these fermions to bosons. So this is a standard technique. And basically, you write each component, which is a fermionic component. You can write it the exponential of some bosonic field. This is in CFT, this is like Coulomb gas or something, yeah. And then you can, with these components, you can define phi left and phi right. And these are like the left moving and the right moving bosons. Then you can put them together, you can define this massless boson. And then you can define another field which will be useful later called theta. Okay. So in the continuum limit, what we obtain is the following. So we have two Ising chains described by two Ising CFT, and then you couple them in the z direction by this sigma 1 and sigma 2, which correspond to some spin operators on the lattice. And by standard bosonization techniques, you have this dictionary. So for example, this if you want to write this thing in terms of bosons that we introduced in the previous slide, this will be cosine phi divided by 2. So you can write this, and then you find that the theory you find is that this kinematic term will be this partial phi square, and this interacting term will become this cosine beta phi with beta equals to 1/2.
Yeah, but both Isings, they are critical, right?
Yes. Both Isings are critical, yes. Yeah. So this looks like what? This looks like a sine-Gordon theory at beta equals to 1/2. And we are familiar, and we like sine-Gordon theory. But it's slightly different, as Alyosha pointed out, because two copies of Ising is not completely equivalent to a free complex Dirac field. You need to model out some symmetry. So precisely speaking, this theory, which I will call like Ising square theory, is slightly different from the sine-Gordon at beta equals to 1/2, because this Ising square is more like defined on some Z2 orbifold, and then this Ising, this sine-Gordon is more like defined on a circle. So this will make some difference, because although the action looks the same, but the difference, there will be some difference, but the difference is minor. So you will find some signs only by some minor signs in the S matrix. So you can take this sine-Gordon at beta equals to 1/2. This corresponds to some reflectionless point. In general, sine-Gordon has a reflection. But at some special points, the reflection is vanishing, so it becomes some diagonal scattering theory again. And this is one of these points. It's beta equals to 1/2 in my notation. And then you can write down this S matrix of all this S matrix easily. And you compare with this Ising square, which has been studied, you see that there are only some sign difference. Okay, so then our strategy is clear. We want to use our knowledge about sine-Gordon at beta equals to 1/2. So this sine-Gordon at beta equals to 1/2 has been studied because it's a reflectionless point. It's easier to solve than generic beta. And then we can find the form factor of sine-Gordon. It has been studied, for example, in this paper by Lukyanov and Lukyanov-Zamolchikov. They studied these form factors.
Say in terms of free simple one conforming field theory, what is this point, beta 1/2 in the normalization reflectionless. So there is this classification, yeah, which consists of a circle line, overfold line, which touch to each other, self-radius, if I remember, yeah.
Radius.
So who is this beta 1/2?
So we can.
It's probably not so dual, yeah?
No.
Maybe it's fermionic or what?
C equals minus 2.
C equals to minus 2? How can it be?
1 minus 2. It's radius 1, but we can check this. Yeah, we can check. So, and I said there's the difference between this guy and the Ising square is some minus sign in S matrix. So then you can try to solve it. And then if you know the solution for the sine-Gordon form factor, then you just do some simple deformation, namely multiply some factors that takes into account this minus sign. Then you can find this Ising square form factor. And then you can compute this. So I'll say a bit more about this Ising square theory. It also has 8 particles. So this has been studied in a paper by Musardo and the collaborators. There they studied a more general situation. You couple 2 CFTs by some relevant deformation which couples the 2 theories. So this belongs to one of this type where you can do some quantum group reduction. So anyway, it has been studied. We know that it has 8 particles. They correspond to, in the sine-Gordon theory, correspond to 1 soliton, 1 anti-soliton with this mass and also 6 breathers. So it truncates. So you only have 6 breathers with this mass. And this mass spectrum is related to some DA1 algebra. So this is their S matrix. So the scattering between a breather and this is soliton, this is anti-soliton, is given by this factor, where this alpha is this typical solution from S matrix bootstrap. And this scattering between the breathers are also given very explicitly in this S matrix. So then you use this as an input, you solve the form factors, and so on and so forth. So what kind of operators we are concerned now? We want to study the spin dynamics. So for example, in the x direction, because now you have 2 chains. So you want to S1x, S2x, take the sum or subtract them. So you can find these fields, cosine phi and cosine theta, which are the fields appeared in bosonization. So you want to compute, if it is a cosine, this is a cosine, then you want to compute some exponential, the form factor of this exponential of bosons. So these are like the vertex operators that you want to study. And this you can construct it, and we can first take the sine-Gordon theory result from Lukyanov, and then we multiply some extra factors to take into account these minus signs, and we can compute the 1 particle, 2 particle, 3 particle form factors. Then we can compare with the numerical result by ITBD. So that's what we found. You find basically, again, the analytical result, which is computed by form factors, matches quite well with the ITBD numerical result. And okay, so this is the result where we take Q equals to 0. So yeah, so the dynamical, the DSF depends on omega and Q. So here if you take Q equals to 0, then this will be a function of omega only. That's why you can plot this like that. Now, suppose you take a generic Q. Suppose generic Q, generic omega, then you need something to denote the strength of this D. Then you make this color plot. Okay? So this is the direction. This direction is Q, and that direction is omega. And then you use different color to show the strength of that D omega Q. So if it's bright, then it means that if it's close to red, it means that this is very likely. The strength is big. If it's very black, then it's almost 0. And from here you can see these colors. You can see clearly there are some lines. which signifies that there are some particles showing up. Because at q equals to 0, what you can see is the mass. But at different q, you can really see the dispersion relation, the full dispersion relation. Okay? So you see this, you can measure, or you can see these lines. You find that these correspond to some soliton, anti-soliton mass, and this corresponds to some two-particle state. But, okay, you see something. Something is missing. This B1 is supposed to be there.
What is B1? Can you say?
B1 is the, okay, breather. So there are 6 breathers from B1 to B6. And the B1 is the lightest breather, which you should see, right? If it's there, then you should see as one of the peaks or one of the lines. So, but we do numerical calculation and analytical computation. So this is a point where you're supposed to see a peak for B1. But you don't see it. You don't see it here, you don't see it here.
Experimentally, you don't see it even experimentally.
Yeah, at least theoretically we don't see it. So that's an interesting point. And then B3 also we didn't see it. So we find something funny. Where does B1 go? Because if it's in the spectrum and you don't see it, then what can be the possibility? The possibility can be that there might be some selection rules, although the particle is there, but the form factor is somehow vanishing at this value. At this B1, when you take the one particle, and this one particle is B1 precisely, and I will explain why, one of the explanations. So here the fact is that you do an honest computation, you don't see B1, and also you don't see B3 and B5, these breathers, which are supposed to be there. Yeah, so then we talk about some selection rules. So we know that in Sine-Gordon, which is inherited here, we have some charges, some topological charge, which Q, and we know that these solitons have +1, and anti-soliton has -1. The breathers are neutral for this topological charge. And then this fuse, because I'm considering the form factor of this fuse. So this fuse, phi will commute with Q, and then theta will add or subtract 1 unit of topological charge. Now, in addition to that, we also have this kind of parity conjugation, charge parity conjugation. So this operator acting on A plus will make it A minus, acting on A minus will become A plus, and then acting on this breather labeled by n will be given by -1 to the power of n. And it commutes with cosine theta. So from here you see that if you take a B1 state, one particle state, B1, and act with a cosine theta, so this is a state with a 0 topological charge, that's okay, but it's C odd, because n equals to 1 is an odd number. So it's C odd, but the vacuum state itself is a C even. So that's like the selection rule. With this selection rule, this has to be 0, and it's consistent. That's why we don't see also B3 and B5. So this just said, what does this equation tells us? This equation tells us, so this cosine phi, remember, it corresponds to some spin in the x direction. This just tells you this B1 cannot decay via some SX channel perturbation. So it cannot decay from this to vacuum by some x direction perturbation. And further analysis show that it can also not be decayed via SY and SZ channel either, because this is the plot for DSF in the Y direction and the Z direction. Still, this B1 is missing. So again, it cannot decay through the Y channel and Z channel.
This form factor is just exactly 0, right?
In the X channel is exactly 0. In the Y and the Z channel, sometimes it's suppressed by 1 over n, where this n is the length of the spin chain. So in the thermodynamic limit, it's completely suppressed. Yeah. In the X channel, you can argue it away by this selection rule. Yeah. But it's a fact that by doing this computation, we find that this B1, you just cannot decay. It just can't decay via local spin Sx, Sy, and Sz. So this means this guy is very, very stable. Whatever you do locally, you cannot change it. It doesn't decay. But you can produce it. You can produce it, say you can first produce some soliton or anti-soliton, and then by tuning these thetas properly, there's some non-zero chance that you can these solitons can decay via some channel to this B1 particle. And B1 particle is the lightest particle in this theory. So you can see we have an interesting situation where we have a very stable particle which does not decay. You can produce it, and then by first producing some soliton, and this soliton will decay and become some B1. And then this B1 cannot decay anymore. So
it can decay in soliton and anti-soliton?
No, because soliton and anti-soliton is heavier than this guy. So this is the lightest particle which cannot decay. This is something very, very interesting because it's very stable, so we call this kind of thing a dark particle. And in condensed matter, if you can find some kind of particle which is very, very stable, then usually this is a useful thing. People will claim, well, that you can try to use it for quantum computation, like topological charge, but people make this claim a lot, but still, it's a non-trivial fact that in this theory, this particle is very stable against any local spin perturbation. Okay, so then previously I want to compare with experiments. So here is the comparison. This is the comparison of DSF with a single Ising chain and experimental data. So this is a single chain. This is the experimental data. You see there are some peaks. Some peaks are coinciding, some peaks are not. And the ratio between the first two peaks is M2 divided by M1. For the Ising is 1.61a. For this, no, this should be Ising square. Ising ladder, so there's a typo. For Ising ladder, the DSS is more like this, so TFI ladder. So then you can also measure the ratio between the first peak and the second peak. So in the Ising ladder, the first peak is the first peak will be, one of these peaks here will be M1 plus M soliton divided by M2. So this guy is 1.665, which is not so far from 1.618. So just by experiment just tells you it's somewhere around 1.6. So just from this data alone, you cannot really tell whether it's E8 physics or it's D81 physics. D81, yeah. So our conclusion is that a more careful observation of the full spectrum, including M3, M4, is needed. So far we cannot say for sure that this physics, this material describes EA physics. It's possible that it describes D81 physics. So we still need to see, the story is not end. So that's like what we investigate. So with this I will conclude. So we see that this Ising model.
But other peaks, can you have an explanation for other peaks? I mean,
does D8 theory explain other extra peaks other than the last one? Does the D81 theory explain this other extra peaks?
Yeah, it explains some of this satellite piece. Yeah, yeah. Still, you need to, because in this region things becomes blur. In this region, because this region is a continuum and.
This red, I don't understand. This is numerics or this is some kind of analytic?
This is analytic and yeah, form factor calculation.
Yeah, actually, you know, if you call it D81, then you also has to call E81 because that theory is also
good. Yeah.
fine.
Yes, yes.
One should be in both places.
I should be careful with that. If I remember, I give a talk in the mathematics department. I was taking a sloppy physicist attitude, which I shouldn't. Anyway.
E8 is E81,
yeah.
but not D81 is E81, yeah? So this is different.
Good point. Thank you. Anyway, so yeah, the key point is that there's this emergent integrability which happens at Ising away from criticality. And it's very interesting. And there are some experiments which we can try to observe this emergent integrability. So this is real life integrability. And if you take into account some interchain interaction, we should arrive at some emergent D8 integrable theory. And then we study this theory both analytically and numerically. And the interesting observation is that in this E8 theory, we find that the lightest particle, this B1 breather, is very stable against any local spin operations. So there are many things we want to do in the future. First, of course, to pin down whether it's really E8 or D8, we need a more careful study of the full spectrum, both experimentally and theoretically. And just for this D8 theory, there are more theoretical study are needed and can be useful. Because if you imagine, like, suppose you have two chains completely decoupled. This means you have some E8 physics. But then you couple them together in the Z direction, you flow them, it becomes some D8-1. So is there some flow like this which connects these two theories? And then can we say something about this interesting theory?
You mean flow between decoupled E8
and yeah, there's two copies of decoupled EA. And this.
On that picture, you just picked two, but you had many. Probably you have to consider happening for 3 or 4 or whatever.
Yes, that's also being investigated. It's just becoming more and more complicated, but in principle it's possible, like doing 4 chain.
The value of these couplings, I mean, do they know from experiments? Can you estimate them? Or?
Yeah.
You said that, I remember, you said that red coupling is bigger
than the blue coupling, yes.
No, it's experimental.
Yeah, this is experimental, you can measure that, yes. Okay, and then what about these dark particles? Now we just know they exist, so can we make use of it? Can we manipulate these particles if we want to make it useful in any way? So yeah, with that I will end. Thank you very much for your attention.
More questions?
So, is it somehow possible to experimentally access this dark particle?
That's a good question. That's a good question.
So nobody knows?
Nobody knows so far.
Yeah, probably it shows up probably in some other two-point functions. Probably not.
You need to organize such experimental setting that it would appear.
Yeah, that's what we want to do. Like first theoretically, we need to predict how can we first produce these particles and manipulate them in some way. Then we can tell the experimentalists what to measure, what to do. Yeah. But this work has just appeared on arXiv this February. So far we didn't ask experimentalists to do anything. But I hope I did this job of closing a little bit this gap between mathematical physics and real-life experiments, to showing that it's beautiful physics can appear in real material. Yeah.
Do we expect to find some integrable theory to explain all these peaks, or it may be not integrable?
That's also possible, because in material everything is approximation. It can be that they are due to some other effects. So in this kind of experiment you can never be like extremely precise, like perfect. So we just do a little bit better. So suppose first you do one chain and you find that some peaks are not explained. Okay, then we take 2 chains, it did better. And what about some other peaks? Maybe some other effects. And this. Yeah.
Do we know, like, can it be 3 chains interaction explained by some integrable model, or for 3 chain there is no integrable model?
I think for more chains, it's not that much investigated, but in principle, following these ideas of coupling 2 CFTs together, maybe you can do something with more chains. Numerically, if you use ITBD, there's definitely not that a big deal. It's similar. So you can first investigate numerically and then probably do something more analytically. So numerics gives some results very quickly, but doesn't give understanding. So theory really gives understanding, like particles and so on, gives a picture. Yeah.
You know, this E8 theory somehow is described by what's called Boole dot model, yes?
Yeah.
So in this, I mean, do you have an explanation in terms of two couple of Boole dot models and this perturbation? So in total we have two fields, right, and some special perturbation. Should be also some integrable total field, right?
Yeah.
Which one do you know? Okay, can you,
So that's the.
Speaking of thinking of Vadim's question, if you have three Boole dot model, probably it's also something.
Yeah, that's the kind of question we theorists now can try to answer. Because if you don't consider this material, why on earth would you consider couple three chains together? But now you have good motivation of doing that, like coupling four, and see what kind of theories can I obtain. Is it integrable? Is it not integrable? So if it's integrable, is it related to some non-integrable theory, like Sine-Gordon at some other point? If it's related to Sine-Gordon, can we compute the DSF? And then we can make comparison, meaningful comparison with experiments. So that gives the motivation for theoretical studies. Okay.
So maybe I missed. So when we consider several chains, this specific form of interchain interaction, I think you said it's basically what people know from experiment, right? So this it's the dominating.
Yeah, this is the dominating one. Yes.
So it's also like a lucky coincidence. So
Indeed.
this
Indeed.
Yeah,
this is a lucky coincidence, I would say, because if you couple two models in an arbitrary way, it's not guaranteed that you'll find some integrable model. That's for sure. Yeah. So now you just imagine what about this and that and more.
I would say it's even, how to say, it's a miracle, yeah, that the integrable.
Yeah.
Generally.
Yeah.
And then this called atom experiment. I mean, these called atoms, they're not just for fun, but they kind of try to produce some, this quantum computer out of it. And what you said about this state.
This is not code atom. This.
I understand, but you also mentioned it.
Yes.
So there are also some spin change, not in this type, right?
They can engineer the Heisenberg one.
Heisenberg,
not the Ising. Well, probably they can also do Ising if you tune the anisotropy big enough. So what they can actually first do is the Hubbard. Because you can confine these two-state atoms at each site, and then it's like with two spins. And then you just take the strong coupling, if you take the strong coupling limit of Hubbard, you get XXZ. At half filling, you get XXZ. That's one way you can engineer this. And there they can do more things, because cold atom, then you can consider like 40 atoms in the optical lattice, and then you can perturb it, see how this how things evolve. So there you measure different things. Of course, DSF is always something important to compute.
Thank you.
It's a pity that you weren't able to come on Monday, since we discussed this introductory part at our student seminar. Would be very, very, very useful, maybe.
Okay.
Thank you.
Thank you.